We are the Yakamoz UAV team. Our team consists of 6 people and is divided into 6 units: computer vision, autonomous software, mechanics, avionics, ROS, and communications unit. The Fergani UAV is fully autonomous and has 5 motors, 4 vertical and 1 horizontal. It can perform vertical landing, takeoff, and area scanning maneuvers with its 4 vertical motors and uses its tail motor for navigation. The Talon model of the XUAV brand was used as the base of the fuselage, and modifications were made depending on the mission requirements. Fergani, which has an average battery life of 40 minutes and a communication range of 40 kilometers, is designed to carry its payload and autonomously recognize a target, then drop its payload when it reaches the drop point. It has a 6.3 feet wingspan and a fuselage length of 3.6 feet, and it is designed for long-distance gliding. The avionics systems of the Fergani UAV is designed to be compact and modular. All actuators, sensors, and control components are connected in such a way that they can be easily removed and installed and can be quickly replaced if necessary. A 6-cell, 22.2 volts lithium polymer battery with 22,000 mAh load capacity was chosen for the completion of the mission and to provide long flight time. SUAS V4014 motors, which are highly efficient and will provide the required thrust, were used as vertical landing and takeoff and drone mount motors, and Skywalker 80 amp was selected for the ESCs that will feed the motors. SUAS X4130 was chosen as the tail engine for its high thrust, and Flycolor's 150 amp was chosen as the ESC. An emergency power cutoff switch is included on the top of the housing to be able to manually cut off the power if an emergency arises. The ground control station uses the telemetry and Wi-Fi for communication units. The necessary mission commands will be sent to the aircraft through the ground control station with the interface software and connected communication systems. The aircraft's position, location, altitude, airspeed, and the shapes it sees are designed to be displayed on the ground control station screens. Between the aircraft and the ground control station, a two-way connection must be established. This two-way connection starts with the transfer of telemetry data and camera images produced by the aircraft to the ground control station. At the same time, the necessary commands from the ground control station to the aircraft are transmitted through this connection. The aircraft communicates with the ground control station via 3 different frequencies, in 3 different wireless ways. The 5.8 GHz band is used for image communication and transmission. The RF 868 MHz band for the transmission of telemetric data, and the 2.4 GHz band is used for the safety pilot to take control of the system in case of emergency. Within the scope of the autonomous flight mission we undertook in the competition, Fergani VTOL UAV will take off from the runway in rotary wing mode, and after reaching the required stall speed, it will move in fixed wing mode to the area where the payloads will be dropped. After reaching the region, it will switch to drone mode, and the region will be scanned sequentially. During these scanning activities, appropriate payloads will be dropped on the detected targets. In line with the task given to us by the competition, the drop-offs will be done sequentially by loitering 4 kilometers. Throughout the project development process, software tests were conducted in Gazebo 7 simulation environment. In line with the tests carried out, improvements made in the software were aimed to keep the aircraft in the air in the most appropriate way. Fergani UAV is designed to carry 5 8-ounce water bottles and will release its cargo with a parachute. The release mechanism is designed as a rotary system, and only the parachute is attached to the water bottles that fit into their slots without any other mechanical parts. In this way, opening the water bottle release with the parachute is as easy as turning the lid. For the release mechanism, the water bottles, which are placed in a round slot in the rotary part that is placed in a static body and rotated with the help of a servo motor, are designed to work by rotating them so that they correspond to a hole under the static body where a single bottle can fit. 5 water bottles are placed on a drop mechanism which is stationed at the center of gravity with a weight of approximately 2.5 pounds or 40 ounces and are designed to minimally affect the balance of the vehicle during flight. After takeoff, a fixed-wing flight will be performed until the drop zone, and when the area to be scanned is reached, the UAV will switch to drone mode, the terrain will be scanned, and the drop zone will be recognized with the image processing algorithm. During the scan, if the drop zone is discovered, the UAV will switch to hover mode and drop the payload from a height of 80 feet. When the payload starts to fall, the folded parachute of the payload will open with the wind caused by the free fall, slowing the fall and dropping it as close as possible to the required area without damaging the payload. To detect the shapes, it was decided that deep learning-based algorithms would be used because they provide clearer results. Considering these conditions, SST, YOLO, and faster RCNN object detection algorithms were found in the research. SST algorithm is based on deep learning and uses CNN architecture. The main feature of the SST algorithm is that it detects and localizes the object in one go. And since it uses single network, it takes a short time to train. Since the faster RCNN algorithm takes the image through long processes while identifying objects, the need for a new model has emerged. YOLO, which emerged in line with the needs, is another improved object recognition algorithm using deep learning. When the algorithms were compared, it was concluded that the YOLO algorithm and its versions provided better performance, FPS values, and accuracy values, and it was decided to continue training on YOLO. To detect objects, a training set is needed first. It was decided to train from YouTube videos and our image recordings. The train set consists of 4,588 as train set, 1,314 as valid set, and 655 as test set, with a total of 6,557 images, and the algorithm was first decided to be trained in Google Colab environment. But the graphics card provided by Google Colab was insufficient compared to the graphics card we have. As a result, training was done with the NVIDIA RTX 3080 graphics card. The trained artificial intelligence task software was made functional by using the OpenCV library. The task of the robotic operation is to control the data received from the aircraft environmental components on the flight control computer. The computer vision algorithm written in the mission computer determines the time to drop the cargo and completes the mission by transmitting the necessary orders to the flight control computer. Controlling the aircraft's flight by effectively processing and utilizing the data received from the aircraft's environmental components is of paramount importance. This task covers a critical and challenging area, especially in the development and processing of computer vision algorithms. To minimize the breakage risk of the aircraft, the aerodynamic flow analysis of the wings was performed using the ANSYS program, followed by the airfoil analysis of the aircraft using XFLR5 program, and the necessary improvements were made to ensure a more durable and effective design of the wings. These analyses aimed to reduce the risk of breakage by increasing the aerodynamic efficiency of the aircraft. In this way, the safety and performance of the aircraft were significantly increased and its operational efficiency was maximized. The Fergani UAV was designed as a VTOL drone to ensure a stable and balanced takeoff in difficult weather conditions and different terrain types, and to be able to be used as a quadcopter drone to make it easier to scan the area before dropping cargo and to drop cargo afterwards. Motor performance and energy consumptions were evaluated by observing the current draw of the motors. The energy efficiency of the aircraft was analyzed by correlating these data with the time in the air. In line with the data obtained, it is aimed to increase the performance of the aircraft by making the necessary updates. PID control systems are used to stabilize the aircraft and ensure that it follows the desired course. In these tests, the stability and maneuverability of the aircraft were tested by adjusting the parameters of the PID controllers. In particular, the focus was on their ability to smooth out possible fluctuations during flight. The autonomous takeoff tests are where the systems required for the aircraft to take off autonomously are tested. During autonomous takeoff tests, the ability and safety of the aircraft to take off spontaneously are examined. This is particularly important for UAVs. Autonomous navigation tests are conducted to evaluate the aircraft's ability to follow a given route. During these tests, it is examined whether the aircraft follows the desired route using GPS and other navigation systems. In addition, the ability to detect and avoid potential obstacles on the route was also tested. The autonomous landing test is the phase where the system required for the aircraft to land autonomously and safely are tested. During the autonomous landing tests, whether the aircraft accurately targets the runway, landing speed, and other parameters are examined. This process is important to determine the aircraft's ability to land safely even in extreme situations and unfavorable terrain. In the load drop tests, the ability of the aircraft to safely drop a specific load is tested. These tests, which are essentially important for unmanned cargo aircraft, ensure the load is dropped without disturbing the balance of the aircraft and falls towards the point where it is dropped. The success of these tests increase the usability of the aircraft in the field of logistics and transportation. Successful completion of these tests aim to improve the reliability and performance of the aircraft, leading to better results in the future flights. And with this, the video comes to an end. We are confident in our drone as we believe she will proudly represent us in the air. With the hopes of meeting at the competition, all the best.